Welcome to Kotway. In this bustling Kampala economy, running a successful carpentry workshop means making the most out of limited resources. Today, we are going to figure out exactly how many wooden chairs you need to build to maximize your total profit, given strict limits on both your available wood and labor. This diagram shows our two products. To find the perfect production balance, we use a mathematical method called linear programming. We will assign the variable x to represent the number of standard chairs we produce, and the variable y to represent our deluxe chairs. To solve this and any linear programming problem on your UNEB exams, we must follow 4 strict steps. 1. Formulate the equations. 2. Graph the limits. 3. Evaluate the corners. And 4. Conclude with the optimal numbers. Let's start with step 1. If you try to skip straight to calculating profits without clearly defining your constraints, you will almost certainly get the wrong answer. Translating the physical limits of your workshop into mathematical symbols is the required foundation for everything else. This animation translates our physical limits into math. Let's look at labor. The workshop has at most 40 hours of labor available. Since a standard chair takes 2 hours and a deluxe takes 4, we write 2x plus 4y is less than or equal to 40. We can simplify this by dividing everything by 2, giving us x plus 2y is less than or equal to 20. Next is our material limit. We only have enough wood to build 24 chairs in total. This simply translates to x plus y is less than or equal to 24. The market also dictates that deluxe chairs, RY, must be at least 1/3 the number of standard chairs, so y is greater than or equal to 1/3 x. Finally, because we cannot physically build negative chairs, both x and y must be greater than or equal to 0. This stack of abstract inequalities now perfectly represents the exact physical boundaries of our workshop. With our rules set in stone, we are ready for step 2, graphing. This Cartesian plane is where we plot our constraints. By setting an appropriate scale, we can draw our first solid line for the labor limit, x plus 2y equals 20, by connecting its intercepts at 0, 10 and 20, 0. To figure out which side of this line represents our allowed production, we test the coordinate 0, 0. 0 is less than 20, which makes it true. But remember the critical UNEB rule. We always shade the unwanted region. Since 0, 0 is valid, we shade the opposite side to block out the forbidden area. We apply the exact same logic to our material line, x plus y equals 24, and our market demand line, y equals 1/3 x. By shading out all the areas that violate our limits, the remaining unshaded polygon in the center forms our true feasible region. Every single point inside that clear, unshaded shape represents a physically possible combination of standard and deluxe chairs that we can build with our current resources. Look closely at this feasible region. According to the corner point principle, our maximum possible profit will never be sitting in the middle of the shape. It will always hide directly at one of these outer vertices. Now it is your turn. Pause the video here and use simultaneous equations to calculate the exact coordinates where the labor constraint intersects with the market demand line. Welcome back. If you substituted y equals 1/3 x into the labor equation, you should have found the intersection exactly at the coordinate 12, 4. Our other two viable intercepts are 0, 0 and 0, 10. This brings us to step 3, evaluation. We introduce our objective function, 20,000 shillings per standard chair plus 30,000 per deluxe chair. Now we simply plug our corner coordinates into this profit equation to see which combination wins. This table compares the outcomes. Producing nothing yields 0 profit. Building 10 deluxe chairs gives us 300,000 shillings. But the combination of 12 standard chairs and 4 deluxe chairs maximizes our equation, pushing our profit up to 360,000 shillings. Before we lock this in, we have to verify our integer constraints. You cannot sell a fraction of a wooden chair. Fortunately, 12 and 4 are whole, clean numbers, so our solution is perfectly valid. This local currency represents our ultimate goal. Step 4 is our conclusion. To hit peak efficiency, produce exactly 12 standard and 4 deluxe chairs, delivering a maximum profit of 360,000 Ugandan shillings. Mastering linear programming is just a matter of following the process. Formulate the rules, graph the limits, evaluate the corners, and conclude your findings. For more UNEB practice problems and step-by-step guides, visit us at yaka.cc.